Hello, I'm Laura Marshall.
And I'm Melinda Rose, and this is Light Matters for September 26, 2012.
On this week's show, squeezed light measures a moving target, a laser shatters the electromagnetic bottleneck facing EPR spectrometers, lensless imaging tracks thousands of cells, inkjet technology prints lasers, and the EU invests in an ambitious laser project in Romania.
Theoretical physicists in Tokyo and Australia pushed the boundaries on ultra-precise measurement by developing a quantum mechanical technique to track the waveforms of photons. Ultra-precise quantum-enhanced measurement has been done before, but only with very small phase changes. This new work tracks large phase changes as well. The key to their work was combining phase squeezing of light waves with feedback control to track a moving phase better than previously possible using laser beams of the same intensity. Their results hint that the quantum mechanical technology may have practical applications for optical communications and metrology. They also discovered that it is possible to squeeze light too much, and that squeezing it beyond a certain point actually degrades the performance of the measurement, making it less precise than if they had used completely unsqueezed light. The research appeared in Science.
EPR, or electron paramagnetic resonance spectroscopy, has existed for decades, but it's been limited by the electromagnetic radiation source it uses to excite electrons. Now, a multi-university team used the University of California, Santa Barbara's free electron laser to shatter the electromagnetic bottleneck EPR has faced. They used 240 gigahertz of electromagnetic radiation to power an EPR spectrometer and yielded a more efficient tool for revealing details about the structure of targeted molecules. The team, which includes researchers from UCSB, USC, and Florida State University, used the technology to study the electron spin of free radicals and nitrogen atoms trapped inside a diamond. Breaking the bottleneck enables electrons to report on faster motions occurring over longer distances than ever before. The work could lay the foundation for discoveries like new drugs and more efficient plastic solar cells. The findings appear in Nature.
A novel lensless computational imaging platform is being touted as a new way to observe and track large numbers of rapidly moving objects under a microscope, capturing precise motion paths in 3 dimensions. For the first time, the 3D helical swimming patterns of more than 24,000 individual human sperm cells were directly recorded for as long as 20 seconds over wide fields of view and through large sample volumes. The work was done by a team at UCLA led by Idawan Ozcan. Observing human sperm cells has generally been limited to conventional lens-based optical microscopes. The small size of the sperm head requires a high magnification lens to observe its motion, and the sperm cell's relatively fast speed makes it difficult to track them over time as they move in 3 dimensions in and out of the microscope's small observation field. To address these challenges, the UCLA team developed a computational lens-free on-chip imaging platform that uses the holographic shadows of the cells. Lens-free images of the cells were acquired simultaneously using red and blue light. The offset light beams create holographic information that, when processed using sophisticated software, accurately reveal the paths of the objects moving under a microscope. This multi-angle, multicolor illumination setup allowed simultaneous and very accurate tracking of the 3D motion of approximately 1,500 human sperm cells per experiment across a wide field of view of 17 square millimeters. The holographic technique could accelerate drug discovery and prove valuable for monitoring pharmaceutical treatments of dangerous microbial diseases. The research was published in Proceedings of the National Academy of Sciences.
Using everyday inkjet technology, scientists have designed a process for printing an organic laser on virtually any surface. The development has wide-ranging possible applications, including biomedicine and displays. Most lasers today are made on silicon wafers similar to those used in microchips, which is an expensive process. But the new method, developed at the University of Cambridge, uses technology similar to that used in many homes. Their approach involves developing lasers based on liquid crystals. If aligned properly, the helix-shaped structure of the LC molecules can act as an optically resonant cavity, which is an essential component of any laser. After adding a fluorescent dye, the cavity can be optically excited to produce laser light. Using the custom inkjet printing system, the researchers printed hundreds of small dots of LC materials onto a substrate covered with a wet polymer solution. As the solution dries, the chemical interaction and mechanical stress cause the LC molecules to align and turn the printed dots into individual lasers. The process was initially developed to produce compact, tunable laser sources and high-resolution laser displays. However, it can also be used to print fluorescent, tag-based lab-on-a-chip arrays used extensively in biology and medicine. The research appears in Soft Matter.
The European Commission recently approved nearly 180 million euros for a new laboratory in Romania that will study laser-based nuclear physics. The funding for Extreme Light Infrastructure Nuclear Physics, or eli-np, will be provided as part of a broader initiative with the Czech Republic and Hungary to form a pioneering European research consortium. The eli-np, to be built south of Bucharest, will consist of a very high-intensity laser and a high-intensity beam generated by combining laser light with an electron beam from a linear accelerator. It is expected to be operational in 2015.
Well, that's it for this edition of Light Matters, Photonics Media's weekly newscast. We'd like to hear from you. Tell us what you like or don't like about our program. We welcome your comments and suggestions at lightmatters@photonics.com.
You'll find links to share and subscribe to Light Matters by clicking the Share with Friends button on our video player.
Thanks for watching, and we'll see you next week.